Start here. Well, welcome everyone, and I apologize for being a bit late here. So what I'd like to do this morning is just give you a quick overview of carbon in the oceans, if this ever starts up. And I'm sure you'll be getting a lot of this material over again, but that's probably okay. I'm assuming that most of you are familiar with ocean acidification and why we're all here. So I'm going to focus more on carbon distributions and... Come on.
There's no in between, unfortunately. You get all on or all off.
Sorry?
There's no in between.
Oh.
You keep us awake with the lights or your voice?
I'll be loud. Okay, so again, I'll just be talking about the distribution of carbon. Oh, that's not bad, like that. Oh.
It's a gradual.
Okay, I see. Okay, whatever. No. Oh, I don't know what that's there for. Go away. Okay. Whew, sorry. All right, so here's a schematic of the global carbon cycle. The black arrows indicate the fluxes, exchanges of CO2 between the various reservoirs, with the values being in petagrams of carbon per year. The red arrows indicate the anthropogenic fluxes, and this is all an average for the years 2000 to 2005. So of course, the burning of fossil fuels has released on average about 7.2 petagrams of carbon per year. We're up to 8 petagrams now today. We've got deforestation is about 1.5 petagrams of carbon. The forests are actually working as a net sink for CO2 now. They seem to be taking up more CO2 than we're releasing. But of course, our focus is over here on the oceans. And the oceans appear to be taking up about 2.2 or so petagrams of carbon per year. But what I want you to focus on here with this are the values that are in the square brackets here. These are the reservoir sizes. And the thing to note is that if you look at the size, the amount of carbon that's stored in the ocean compared to the atmosphere or the terrestrial biosphere, you'll see that of this kind of three-component system, these are the three components that exchange carbon on time scales of years to decades to centuries, that almost 90% of all the carbon, natural carbon in the world is actually stored in the oceans. And therefore the oceans are key to controlling the global carbon cycle in that respect. So that's why it's important. Now there are two ways that we study CO2 exchanges in the ocean. We can look at the air-sea exchange of CO2, the actual flux of CO2 in and out of the oceans. Or we can go and look at the changes in carbon inventory in the ocean interior. So if we know how much was there, say in the mid-1990s, and we go back later and we measure the carbon distributions again, we can look at those changes, and from that we infer how much CO2 was taken up from the atmosphere. So those are the two basic approaches that we use. For the surface ocean, for the air-sea flux, there's a network of observations using ships, both research ships and ships of opportunity. These are container ships and cargo vessels that are running regular tracks back and forth across the oceans. And we put underway CO2 instruments, like you're going to see this afternoon, on these ships so that they measure CO2. And all these different lines here show the different ship tracks as of last year. We also have CO2 systems that we put onto moorings. These are just some examples shown by the red dots here. That's a network that's just starting to grow, and we'll be showing you an example of one of those instruments on Thursday. So from all those measurements, we've been doing this now for several decades. We can pull all those measurements together, and this is the famous Takahashi climatology of CO2 fluxes in and out of the ocean. The yellows and reds are areas where CO2 naturally is coming out of the oceans. The blues and purples are areas where CO2 is going into the ocean. So of course the equatorial Pacific, for example, is an area of upwelling. So you're bringing up that CO2 and it gets released to the atmosphere. But of course this is just a static picture based on 40 or more years of CO2 observations. And the CO2 is not really a static thing. It actually varies quite a bit by season and spatially. And so it's quite a challenge to get enough measurements to try and measure all these changes. But typically when we're trying to understand air-sea fluxes, the thing that we're measuring out there is the actual CO2 of the water in the atmosphere. And then from that we can calculate the air-sea exchange. When we move to the ocean interior, there's a tremendous data set that was collected in the mid-1990s. Two international programs, the World Ocean Circulation Experiment and the Joint Global Ocean Flux Study, got together and did a global survey of CO2 in the oceans. We measured DIC, or total CO2, to about plus or minus 2 micromoles per kilogram, and alkalinity to about 4. It took 5 years after this cruises were completed. It was nearly 100 cruises. It took us 5 years then to compile all this into an internally consistent data set that we could use to make some global calculations. So let's take a look at some of the other parameters and see what they look like. So this is now a map on the top here of the surface total alkalinity. And one thing I should apologize for right here in the beginning, we tend to use a lot of different shortcuts for the names for the same thing. So I'll just apologize right up front. So you're going to see throughout this week probably people using TA, T-alk, alk, A sub T. All these things are the same thing. It's all total alkalinity. That's what we're measuring. Anyways, well, all right. Hopefully they're the same thing. Anyway, this is the distribution of alkalinity in the surface waters. And what we see is that the alkalinity looks very similar to salinity in the surface ocean, which is shown in the bottom figure here. That we get the same maximums, the same general minimums. The primary difference is that the Southern Ocean tends to be low in salinity, but higher in alkalinity. And actually you can see that this is an example from the Indian Ocean. If we just now are focusing in on the Indian Ocean, where we've got actually the largest range in salinity, all the way from 31 all the way up to 37. This is the Arabian Sea water here, where you've got the Ross Sea and the Persian Gulf releasing very high salinity water, and the Bay of Bengal, of course, has lots of rivers that feed into it, giving it very low salinity water. And generally you see that there's a nice linear correlation between salinity and alkalinity. There's a little bit of an offset here in the bays. That's because the rivers tend to have some alkalinity in them, even though they don't have salinity, so there's a bit of an offset there. But the big thing you notice is the Southern Ocean. The Southern Ocean has a much higher alkalinity to salinity ratio, and that's because of the overall circulation of the ocean. If the deep waters are formed in the North Atlantic, as they sink and then they flow south in the Atlantic, they're accumulating alkalinity as carbonate particles dissolve, and then when those waters get brought back up to the surface in the Southern Ocean, they have higher alkalinity to salinity ratio. Total CO2, we have the same issue with names. You'll see TCO2 DIC, which stands for dissolved inorganic carbon, C sub T, you may even see some more. I've seen sigma T is used. Anyway, all these things hopefully are representing the same thing, which is the total carbon dioxide concentration, actually the total inorganic carbon dioxide concentration. If we look at the distribution of total CO2 in the surface waters, this is what it looks like. Generally low in the lower latitudes and high in the higher latitudes. It looks fairly similar to, it's got a pattern that looks fairly similar to the nutrients in terms of high values in the high latitudes and low in the low latitudes. Of course, the difference you see here is in the subtropics, where you've got moderate levels of total CO2 with no nutrients. What's happening there, again pulling an example from the Indian Ocean, is that we've got a fairly good relationship, but what happens is you run out of nutrients before you run out of total CO2. So then you end up with basically lots of waters where there are no nutrients, but you still have changes in CO2. From these calculations, you've all seen the estimates of anthropogenic CO2 in the ocean. I don't want to spend a lot of time on how we do that, but just very quickly to give you one example of the back calculation technique. If you look on an isopycnal surface, again this is an example from the Indian Ocean. The isopycnal surface from 27.2 to 27.3 sigma theta. The outcrop for this surface is in the Southern Ocean, and it does not outcrop in the north. So if you look along that isopycnal surface, you see that there's about 140 micromole increase in the total CO2s of those waters. Now most of that increase is due to the uptake from the decomposition of organic matter. So we can use a Redfield ratio and remove this biological signal using oxygen in this case. We can also remove the preformed total CO2, so we can calculate what the CO2 would be in equilibrium with a pre-industrial atmosphere of 280 parts per million. When we subtract those two, the trend then looks like this as a function of latitude. Now the change is only about 30 micromoles per kilogram, and you see that it's highest closest to the outcrop. So this is presumably the uptake of CO2 from the atmosphere. Now the one piece that we're missing here is of course that the surface waters are not in equilibrium with the atmosphere. There's some disequilibrium component, and I don't want to get too much into how we calculate that, but using a water mass age tracer and the atmospheric CO2 history, we can come up with an initial guess at what the anthropogenic component is. If we subtract that, then what's left over is the disequilibrium term. And if we've done that properly, then across that whole surface we should get a constant value, which in this case you see is about minus 20 micromoles per kilogram. This is now plotted as a function of the CFC12 age rather than the latitude. But we see that everywhere we get a constant offset of minus 20 micromoles, which happens to be the bottom axis of this middle plot. So now the difference between each of these points and the bottom of this plot is the anthropogenic CO2. So there is actually anthropogenic CO2 throughout this surface with values near the outcrop of about 40 micromoles and values out here that's closer to 20 micromoles. So there are a number of different techniques. They all more or less follow this same idea that you remove the biological component, and then you have to figure out what the preformed values are, which include both an equilibrium component and a disequilibrium component. When we plot those up, we see that most of the deep oceans actually have never been exposed to anthropogenic CO2. The exception to that is the North Atlantic, where you're forming deep waters where that anthropogenic CO2 is actually penetrating all the way to the bottom. But throughout the Pacific and the Indian, most of the CO2 is confined to the upper waters. In fact, we find that 50% of the anthropogenic CO2 is confined to the upper 400 meters. So we're just looking in the surface waters for those. We also see changes in pH, of course. That's the whole thing that got ocean acidification started. It's very, very difficult to see the changes in pH. Seawater is a very well buffered system, so the changes are quite small, but using spectrophotometric techniques, we can actually see it. This is some work that Bob Burns did in the North Pacific on P16 North along 152 West, basically north between Hawaii and Dutch Harbor, Alaska. He did some measurements in 1991 on that cruise. We went back in 2006 and repeated that cruise, and these are the changes in pH that he saw. You can see they range to about 0.08, but on average the decrease was 0.025 pH units between 1991 and 2006. If we look at the distribution of surface pH, this is what we see. It's somewhere in between alkalinity and DIC. You see some low values, very low values at the strong upwellings sites, but that dissipates pretty quickly. So for example, we get upwelling in the equatorial Pacific, but as those waters move across the Pacific, the pH comes back up as you're losing that CO2 to the atmosphere. So you only really see the strongest signals very close to the upwelling centers. You tend to see higher values in areas where you've got strong productivity. So where the biology is drawing down the CO2, that increases the pH of the waters. So the pH is somewhere in between alkalinity and total CO2. If we look at the vertical distribution of pH, the main feature that we see is the pH minimum that's associated with the oxygen minimum. So again, it's strongly controlled by the decomposition of organic matter in the subsurface. So what we can do is kind of look at the three major processes that affect the different carbon parameters. You've got gas exchange, where the CO2 comes in and reacts with the water molecules to form the various ionic species, ocean physics, and biology. And this is just a rough distribution of how the different parameters are affected by the different processes. Total alkalinity is most strongly controlled by the ocean physics. I showed you it correlates very well with salinity, a conservative tracer. It is affected slightly by biology through the uptake and release of nutrients that can affect the total alkalinity. It's not affected by gas exchange. Total CO2, on the other hand, is most strongly affected by biology, but is also affected a little bit by gas exchange and by the ocean physics. The PCO2, of course, is very strongly affected by gas exchange, but also affected by these other things. And pH kind of sits somewhere right in the middle, some combination of all of these. Of course, the issue for us here, and why we're all here, is that basically all of these things are changing over time. Right? We know that CO2 is rising in the atmosphere, so that's going to be changing the gas exchange. We're going to be absorbing CO2 in, which is going to affect this portion of the curve. At the same time, that CO2 that's left in the atmosphere is changing the temperature structure and other mixing parameters that affects the ocean physics. And of course, the CO2 also affects the biology through ocean acidification and other factors. So basically, the distribution of all these carbon species can be affected by rising CO2 in the atmosphere and the associated climate change. So let's take a little bit of a look at that and see what that means. So this is a plot now showing the black line here shows the rate of growth of the fossil fuel emissions over time for the last 45 years or so. And we can see that the rate of fossil fuel emission has grown continually throughout this period. So as I said, today we're up above 8 petagrams of carbon per year being released from burning fossil fuels. We can also look at the growth of CO2 in the atmosphere. You see it's much more variable. That's associated with the interannual variability in the ocean and the terrestrial biosphere that are taking up this CO2. They're quite variable, but in general you see that there's a growth in the atmospheric CO2 concentration. In fact, it's increased by about fourfold over the past 45 years. Now this is what is not being taken up by the terrestrial biosphere or the oceans. So let's take a look at the oceans. We know from the work that Taro Takahashi and others have done looking at PCO2 concentrations over many years, that over most of the ocean, the CO2, the surface PCO2 has been increasing at about the same rate as the atmosphere. There's some variability and there's a lot of uncertainty in these calculations, but pretty much as a general rule, everywhere we look in the surface ocean, with a few exceptions, the surface CO2 is increasing at the same rate as the atmosphere. So we know, I just showed you that the atmosphere is increasing has increased by about fourfold over the past 45 years. So we might expect that the oceans would be increasing proportionately, but in fact they're not. Here are some model results. The heavy black line here shows you a climate model that has a constant climate. It has the CO2 is increasing, but the temperatures are not changing, the circulation's not changing, nothing else is changing except the rise in CO2, and it shows less than a threefold increase in the carbon content of the oceans over that same 45-year period. The other colored lines here actually show the models that do include climate change, and they actually only show an increase that's about half the rate of the atmosphere. There's been a lot of attention paid to this difference recently, the difference between the models that don't have climate change and the models that do have climate change, and the focus on, the uptake of CO2 in the oceans is decreasing. What I actually want to talk about is the difference between this and the atmospheric growth rate. That's a much bigger signal. Why are the oceans not able to keep up with the growth rate in the oceans, in the atmosphere?
Before you go on, just to clarify, so when you're talking about a 2x or 3x or 4x, that's the increase in the anthropogenic carbon in that reservoir, right? I mean,
that's an increase in the, so in the case of the atmospheric CO2 was 280 parts per million. That's the increase in the concentration of CO2 in the atmosphere relative to that pre-industrial value of 280. Okay?
well, it's not, that's what I'm trying to...
That's what it is in the atmosphere. In the ocean, yes, we're looking at the rate of change of the anthropogenic CO2. Right, so there's a very large background CO2 that's constant. We're just looking at the change in the anthropogenic component. Okay? So the reason why the ocean is not keeping up, of course, has to do with the complicated carbon chemistry and why you're all here for 2 weeks to try and learn about this stuff. CO2, when it's absorbed by the ocean, reacts with water molecules to form bicarbonate, which then dissociates in, carbonic acid, which then dissociates into bicarbonate and CO2, or carbonate rather, not speaking well. That also has associated with the calcification. All these things affect the uptake of CO2 in the ocean. So as CO2 rises in the atmosphere, most of the CO2 in the ocean is in the form of bicarbonate. This is about 90% of the CO2 right now is in the form of bicarbonate. About 9% is in the form of carbonate, and about 1% is in the form of CO2 aqueous. Now the CO2, the carbonate ion actually decreases because what happens is that when you take CO2 and water together, you form carbonic acid, which dissociates into bicarbonate. This hydrogen ion at these pHs actually combines with the carbonate ion and forms another bicarbonate. So most of the hydrogen ions that are released from this are being added to the carbonate to form bicarbonate. So you see that the carbonate ion is actually decreasing. Now, it'd be nice if we could understand the relationship between the uptake of CO2 and that carbonate chemistry. And that actually was first introduced by Ravel and Suess back in 1957. They generated this thing called the Ravel factor, which looks at the change in CO2 given a change in DIC. This is the distribution of the Ravel factor in the oceans. You see it's high in the high latitudes and lower in the low latitudes. What this means is that the lower latitudes are better buffered than the higher latitudes and are more efficient at taking up CO2 than the higher latitudes. The problem with this is that this Ravel factor cannot be explicitly calculated given the way that the formula is put together. So what we've done, this is some work that I've got in press in Global Biogeochemical Cycles, and I can, this wasn't in your reading material, but I can give it to you later. This is some work that I've done with Francois Morel, where we've gone back now and derived 6 buffer factors for the oceans to help us better understand the carbonate chemistry. And these are factors that can actually be explicitly calculated for any given sample. The first one is gamma DIC. It's essentially equivalent to that Ravel factor, but like I say, it has the nice feature that it can be explicitly calculated. And in fact, if you take DIC, the measured DIC, divide it by this gamma DIC, then it is numerically equivalent to the Ravel factor. So this tells us, this relates the change in CO2 to the change in DIC. You can do a similar sort of thing where you can relate the change in CO2 to a change in alkalinity. This is the gamma alk. We've got a beta alk. This is basically just a standard definition for a buffer. It's telling us the resistance of the pH change to a change to an addition of any acid or base. So it's relating pH to alkalinity. Again, you can do the same sort of thing looking at the change in pH to a change in DIC. And then since ocean acidification is an important and interesting thing that we're all trying to understand here, we've come up with another set of buffer factors that relates the change in the saturation state of the waters to changes in DIC and to alkalinity. So let's just quickly look at those first. So this is from a site in the North Pacific with an alkalinity of 2.25 millimolar in the surface waters at 20 degrees. And if we plot, these are the plots of all the different buffer factors as a function of the DIC concentration. Now the one feature that you see that pops out right away is this minimum. We find that all of these buffers reach a minimum when the DIC concentration is equal to the alkalinity concentration, and then it increases. It's higher at lower DICs and it's higher at higher DICs. So what's that about? So this is a plot of the relative concentrations of bicarbonate ion shown in red, the carbonate ion shown in black, and the aqueous CO2 shown in green. And the blue line here shows the distribution of the waters today. So this is as a function of pH. So this is where we are today. So that, as I mentioned, about 90% of the CO2 is in the form of bicarbonate, about 10% is in the form of carbonate, and 9% and about 1% is in the form of CO2. As you add CO2 to the waters, you're pushing this line to the left, right? So you're going to lower pHs, you're increasing the CO2, you're decreasing the carbonate ion. The point where total CO2 equals alkalinity is the point where these two lines cross, right? And so this is where the DIC equals the alkalinity. And at that point, basically, almost all of the CO2 is in the form of bicarbonate. There's very little carbonate or CO2 in the waters. So as you continue to add CO2, this is the point at which you now are starting to titrate the bicarbonate. So now when you add excess hydrogen ions, they're not just changing the carbonate ion to bicarbonate. Now you're actually starting to convert bicarbonate to carbonic acid. So that's why the buffer capacity then starts to go back up sharply, because there's a ton of bicarbonate in the water that you can then titrate back to bicarbonate. So what happens is the buffering capacity goes down, 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 because there's less and less carbonate to turn into bicarbonate. So it's getting harder and harder for those hydrogen molecules to find a carbonate ion to attach to, until you start titrating then the bicarbonate to carbonic acid, and then all of a sudden there's tons of bicarbonate. So now the buffering capacity goes way up, because it's much easier for a hydrogen ion to come up with, to interact with the molecule. So what does that mean in practical terms? So here's where we are in the pre-industrial. As we add CO2, increase the CO2 in the atmosphere, we're basically falling off this cliff, moving down into the minimum for the buffer capacity of the oceans. And as we do that, you can see that all of these buffer factors increase. So let's take a look first at this gamma DIC. This is the one that's equivalent to the Ravel factor, which is this blue line here on the bottom. What we can do then is relate the buffer capacity to the change in DIC that you would expect for a fixed change in PCO2. So what I'm going to do over the next few slides is we're going to increase the PCO2 of the waters by 10 microatmospheres and look at the change in the DIC, right? Because the CO2 uptake and exchange is driven by the PCO2 of the waters, not the DIC concentration. It's the difference between the air, the partial pressure of the CO2 in the air and the water. So if PCO2 is increasing in the water at the same rate as the atmosphere, let's see what a change of 10 microatmospheres does for DIC. And what you see is that the higher this buffer factor, the larger the DIC change. And the lower the buffer factor, the lower the DIC change. Oh, I should just point out, so you see that there's a bit of scatter in this, even for a given buffer factor. The reason for that is because we're basically out here on the level, so the slope of this line is not very steep. So for any given buffer factor, there's actually a range of CO2 values that you can have. But as you fall off, as you move towards this minimum, you see the slope is getting steeper. So that changes, and I'll come back to that in a minute. So here's the distribution of the gamma DIC in the surface oceans. You see it's higher in the lower latitudes and lower in the high latitudes. This looks very similar to that Ravel factor plot that I showed you earlier. And again, what that's showing is that the lower latitude waters are more well buffered than the higher latitude waters, which means that the lower latitudes are going to be more efficient at taking up CO2 than the higher latitudes. But let's look at how this changes over time. So this is in the pre-industrial, and in particular, I'm focusing here on the North Pacific. If you look at this gradient in the buffer factor, watch this number here, this delta. It actually doesn't change as we move to the modern, and then here's a 2x, and here's the 3x CO2. So that the entire ocean, the buffering capacity of the entire ocean is decreasing, but the actual range of that is not changing significantly. So going back to this plot, we can now look at this buffer factor as a function of what the change in DIC, And you see that for the pre-industrial ocean, for a given change in CO2, you've got, at the lower buffer factors, you've got an uptake of about 5 micromoles per kilogram. And at the higher end, you've got more like 11 micromoles per kilogram with a mean that's somewhere around 7 or 8. Now, as we step forward into today, this is the relationship that we've got today. Remember, we're kind of falling off that cliff. We're going towards that minimum in the buffer capacity. So there's actually been a 25% decrease in the uptake rate, in the efficiency of the uptake of the oceans. As we go towards a 2x CO2, we see a 60% decrease in the efficiency of the uptake, and a 3x CO2, there's a 75% drop. And as you can see, that the buffering capacity of the whole ocean is getting lower and lower and lower. And as we're approaching the steeper part of that curve, this spread gets shallower as well. And I see Heather's standing up, so I'm just going to quickly go through. I have one more to show you, and then I'm done. I want to show you this higher slope, which is the buffer capacity for the saturation state of the waters. That's this omega DIC. And we can do the same thing here. You can see that had a much steeper slope, so it's got a much stronger correlation between, and in this case, as you increase the CO2, you're decreasing the saturation state of the waters, right? So in this case, a more negative buffer factor means a stronger drop in the saturation state of the waters. But again, we see this correlation. If we look at the distribution, this is the distribution of omega DIC. We see that the most negative values are in the lower latitudes, and the higher values are in the higher latitudes. This means that the largest changes in the saturation state as you add CO2 are going to be in the lower latitudes. This is exactly where the coral reefs are. The biggest changes we're seeing are right in the areas where the coral reefs live. Now what I want you to look at is this change. Again, this is the gradient in the North Pacific. And you see that in the pre-industrial, we start off with 0.19. Modern, now it's 0.17, 0.13, 0.08. What we're doing is that you're seeing the biggest changes in the low latitudes with very relatively little change in the high latitudes. We're decreasing that north-south gradient in the buffer capacity because the biggest changes are occurring in the low latitudes. You'll see that in this plot. So again, here's the pre-industrial buffer factor versus the change in saturation state. We see quite large changes in the saturation state during the pre-industrial in quite a range. Here we are in the modern. We've already seen a 30% decrease in the saturation state of the waters. As we go to a 2x, we're seeing a 65% drop in the saturation state, and by 3x, we've got an 80% drop in the change in the saturation state with the addition of CO2. So now you see not only this change in the width of it, but we're also seeing a significant change in the height of this. That's the fact that we're decreasing this range. In my last plot, this is comparing now the pre-industrial on the left with the 3 times CO2 on the right. The top plot shows the buffer factor. So this is the omega DIC. You see a very strong gradient in the pre-industrial ocean, and in the modern ocean there's much less of a gradient. And this is now showing the saturation state of the waters with respect to aragonite in the pre-industrial and in the 3x CO2. Again, you see a much stronger gradient in the saturation state of the waters in the pre-industrial compared to the modern. That's because this low latitude is changing faster than the high latitudes, even though you see that by the time you get 3x, you've got undersaturated waters in the higher latitudes. So I will just leave these up, and next we'll move on to Andrew. Do we have time for questions? Or DIC and alkalinity from GLODAP, and then I calculated pH
Okay, okay,
in the surface map.
okay.
The difference in the section that I showed you at the beginning were actual measurements.
Right, that's what, okay, I just wanted to make sure.
Yeah.
Thank you.
Yeah,
Dwight.
I think they made the same plot, if I remember the pH distribution plot that you showed. It showed low pHs along the equatorial tropical Pacific.
Mm-hmm.
But it also showed low pHs on the other side. Is that an interpolation there? On the other side of Panama in the Caribbean, or the Gulf of Mexico, right?
Yeah, that's an interpolation error. We have no data in the Caribbean, so I apologize for that. That was just a quick and dirty plot.
So I really love those plots that you just showed, showing the reduction in the gradient over time. But when you did those calculations, so you started off with the GLODAP sort of distribution of DIC and alkalinity. Did you use a model to predict those changes in the surface, and did you make assumptions about the AOC PCO2 differences?
So for the modern calculations were based just on the GLODAP data. The pre-industrial calculations, I used our estimates of anthropogenic CO2, subtracted that from the measured DIC, and to get the pre-industrial. For the 2X and the 3X, I took the GLODAP data, assumed that the surface water PCO2 would increase at the same rate as the atmosphere to the 2X and 3X. Yeah, so there are lots of other factors that obviously will affect that. I was just trying to look at the CO2 increase. And another subtlety to that is I actually also did that calculation only for waters that were equal to or less than the PCO2 of the atmosphere. So where we have very strong upwelling and we see CO2 that's well above atmospheric, I was not
otherwise you
increasing
probably
those
don't
as
need it
well.
for my
I was
voice.
just looking at the atmospheric CO2 concentration and only increasing those that were